Can you see my pointer?
Yes.
Okay. Okay, so thank you, first of all, Ariel and Luca, for inviting me to give this talk. And I'm going to tell you about the bounds we made on ALP dark matter using data from the optical MUSE-Faint survey and dwarf spheroidal galaxy. And this is a paper I did in collaboration with the team at Turin and part of the MUSE collaboration. Okay, now I don't know how to, sorry, I'm having, I don't know how to move my slide. Can you see the next slide? I'm a bit.
Yes.
Okay, sorry, that's a bit confusion. Okay, so what I'm going to talk about is this bound here in the rectangle labeled by MUSE. And actually, I'm talking about an update of this bound because this bound was already present, but now we improved, let's say, the quality of the bound, and we are more confident in it. Okay, so the bound is based on the axion-photon interaction. As you all know, the axion couples to photon towards the FF dual term, and this can give rise to several processes. One is, for example, axion to photon conversion in an external magnetic field and vice versa. Or what we are looking actually in this paper is the axion decay into two photons. Okay, so this bound is based on axion decay. Sorry, let me try to do something else. Okay, now it works. So the axion decays into photon. There's a decay rate, which turns out to be proportional to the coupling squared and to the mass cubed. And here I put on this plot a dashed line, which marks a line of constant axion decay or constant axion lifetime. And interestingly, like with this optical data, we can basically prove the same axion lifetime as with X-ray telescopes. This seems to be like, I don't know if it's a coincidence or not, actually. Okay, so what's the idea behind the bound we did? So we look at dwarf galaxies. So we have a dwarf galaxies. It has some stars in it, and it has a halo, which we assume to be completely made of axions of a given, or axion-like particles of a given mass. And then this galaxy emits photons, and these photons are going to reach the Atacama Desert, where the Very Large Telescope is. And on the Very Large Telescope, we have mounted the MUSE instrument. Of course, we are not interested in the photons that are coming from the stars, but we're interested in a diffuse emission that comes from the halo. So if the halo is made of axions, some of them will decay, and we hope to detect these photons. So in our images from MUSE, we are going to mask the part containing bright sources. Okay, before moving on, a bit of the kinematics of the axion decay. Okay, it's very simple. So if we, here on the left, we are in the axion rest frame, and the axion carries an energy equal to its mass, m, and each one of the photons will have an energy of m/2, and they are going to be emitted back to back. If we are instead in a frame where the axion has some momentum p, some small momentum p, so that we are in a non-relativistic regime, okay, the energy to linear order in p is still equal to m of the axion, and the photons will be emitted not exactly back to back. So if one has a momentum k, the other photon will have a momentum k minus p, and the energies of the two photons are going to be m plus p parallel over 2 and m minus p parallel over 2, where p parallel is the component of the axion momentum along the direction of k, of the momentum of the photon. So basically, since we have a lot of axions with a lot of momenta, we should expect a narrow line picked at an energy of m/2 with a width which is about equal to the axion momentum dispersion in the galaxy. Actually, but it turns out that for the spectral resolution of MUSE is not enough to resolve this momentum spread. So we're just going to look, basically, effectively, we're just looking for a line at the frequency of the axion mass. Okay, why can't this move? Okay. Okay, so what's the signal? So, oops, sorry. The signal is, so we have the number of axion changes in time proportionally to the axion decay, to the decay rate and to the number density itself. So we can calculate the spectral intensity, which is the power radiated per unit area, per unit frequency, a unit solid angle, like this. So we have, for each decay, we have emitted 2 photons. Each one carries an energy of half the axion mass. And then we have to integrate over the line of sight. And then we have to divide by 4 pi because this emission is isotropic. And then we have it's proportional to the axion decay constant and divided by the beam, the frequency beam we're considering. So we have our telescope here. This is our line of sight. And then to get the flux, we have to also integrate over the beam. This is the experimental beam of the telescope, which sets basically the angular resolution of the instrument. And then, so this is how we calculate our predicted signal. We also added here another Gaussian in wavelength. And this is represents the frequency resolution, the frequency response of the detector, or the wavelength response. And so sigma lambda represents here the wavelength resolution. Okay, so this is how we calculate the predicted signal. I want you to notice that to make this prediction, we need to know the dark matter density profile of the dwarf galaxy. Okay, so what's new in this paper that we put out in July? So this is the title of the previous paper that already used MUSE to make a bound, and this is the bound from that paper that was out in, I guess, in the 2020. So what changed? So this old paper was based on just one dwarf spheroidal, Leo-T, while now we have included 5 dwarf spheroidals in the analysis. Moreover, there was no, let's say, direct information on the dark matter profile of this dwarf, but the integral over the line of sight of the dark matter density was derived from a de facto published in this paper by Bonivard et al. And there were only a few data points and quite a large radii. So basically, there was an extrapolation to be made towards the more central parts of the galaxy. But now, in the meanwhile, the MUSE collaboration has made a GINS analysis to determine the dark matter profile of Leo-T and of the other 4 dwarfs we use, so they look at the velocity dispersion of stars in the galaxies, and these stars are placed much closer also to the center of the galaxy. So we have, let's say, more information about the inner part of the galaxy, and also they gave us the full likelihood for their analysis, meaning that we can integrate this in our analysis in a more rigorous way, statistical way. So these are the 2 main improvements that we introduced compared to the previous paper. Okay, why dwarf galaxies? Well, these dwarf galaxies have typically a high dark matter energy density. So for example, 4 GeV per centimeter cubed, which is about 10 times larger than our local dark matter density, for example. They have a high mass to light ratio, so we don't want something with too many stars in it, because we want to look at light where there shouldn't be any light, in the part where there are no stars. So the dwarf galaxies are a good target for this reason. So here I'm showing a picture actually of Sculpture, which is one of the galaxies we used. Okay, and also they're not too far. They're a distance of about 100 kiloparsecs, so the flux is not too small. Okay, this is the MUSE instrument here. Before it was mounted on the Very Large Telescope. MUSE stands for Multi-Unit Spectroscopic Explorer. So it's a spectrograph, meaning it has a very good spectral resolution, which is what we want because we are looking for a narrow line. So it has it measures in a wavelength range, which allows us to make bounds at the axion mass of order a few electron volts, so 2.65 to 5.27 electron volt. And it's also important that it has a good spatial resolution, because this allows us to exclude from our analysis the pixels that contain bright sources and without losing too much information. Okay, these are the other 4 galaxies that we used. So these are the sculpture is not an ultra-faint dwarf, but the other 4 we used are ultra-faint. This is because observing these ultra-faint galaxies is the goal actually of the MUSE-Faint survey. So we use Grus 1, Leo T, Eridanus 2, and Hydra 2. And from these galaxies, as I said, we have the likelihood for the dark matter profile from this paper here from the MUSE collaboration. Okay, so what would a signal look like in the data? So here what I'm showing is the blue line is for Leo T. The blue line is the average flux in the unmasked pixel of the image. Yes, so average over all the unmasked pixel of the image. And you see there are a lot of sharp lines, and these are lines due to emission by molecules in the atmosphere, like oxygen molecules, OH molecules. And these are, so in the data reduction of MUSE, they attempt to subtract this line, but actually the subtraction is imperfect. So we have this residual emission there. And the green and the red line are what a signal would look like. Okay, so for example, the green one is for axion mass of 3 electron volts and a coupling of 2 in 10 to the minus 12 G inverse GeV. And then we have also the red line at a higher mass, a lower coupling. This red line is higher because even if the mass is lower, the decay rate scales like m to the cube, so we have a stronger signal here at higher masses. Okay, so now you may ask, how do I tell the difference between a signal and an atmospheric emission line? Well, you really can't. So basically, we are able to use this data to put bounds, meaning if there's no line, there's no axion. But it's more difficult to make a discovery, of course. We tried that by excluding all the channels that have a bright emission line. The frequencies of these emission lines are known because they are from known molecules. So for our discovery analysis, we excluded a lot of channels which contain these bright emission lines. And I'm sad to say we didn't find any evidence for ALP dark matter. Okay, but now let's talk more about the bounds. Just a few details about our analysis. So we compute the chi-square using the difference between theoretical flux minus the observed flux in a pixel I divided by the error that the MUSE collaboration gives us. This theoretical prediction of the flux is actually made of 2 parts. So one part is the signal that I described above, calculated from integral over the line of sight, etc. And then we also put a flat term, so a flat constant over the term constant over the image to further model any of these residual emission from the atmosphere. And we let this term float. Like we profile out this term as well as all the other terms that enter the likelihood to obtain a bound as a function only of G for given mass. And then we multiply, before attaining the bound, we multiply our likelihood computed like this with the likelihood that the MUSE collaboration gave us for the dark matter profile. Okay, so this is the result, assuming an NFW profile for the galaxies. So we have the 5 bounds for the single galaxies and the combined one. Oh, sorry. They are more or less all consistent, around 10 to the minus 12 inverse GeV, or a bit better at higher masses. Okay, and this is the result. Basically, this is what goes in the plot of axion limits. Okay, then we also considered a core profile. For example, here I'm showing the best fit profiles, assuming 2 different, the best fit, okay, profiles assuming 2 different models for Leo T. So the blue line is NFW, And the green line is this core NFW tides profile. So it has a core which starts at this radius here, RC. And then it also has a tidal radius, which is not shown here in the plot because it's a large value and it doesn't enter actually in the image. So this is a tidal radius beyond which the dark matter density drops abruptly. Okay, so using this core profile, we also obtain bounds. They are quite similar to the one for NFW. Only the combined bound is only slightly less stringent. Why is that? Because one would expect that for the NFW profile, the bounds to be stronger. Actually, we think that the bounds are similar with these two profiles because the bound actually comes from radii beyond outside the central core. So here what I'm showing is for the core profile for Leo T, the bound in 20 different channels as a function of the integration radius. So the integration radius means that so we have our image centered at the center of the galaxy, and we take some radius around the center, and we consider only pixels within this radius. We make the bound made on these pixels, and then we increase the radius, etc., until considering almost the whole image. And here you see that actually the bound, when you consider only the central part of the galaxy, is not very strong, and it tends to decrease as we go beyond the core radius. So we think this is the reason why the bounds are similar with the two different profiles we considered. Okay, so here's a summary plot. This is our bound main context with other bounds. So this yellow bound is the QCD axion band. Extended QCD axion bound, let's say. Here we have the red line from a stellar bound from stellar evolution, and the green line is bound from another telescope search using VMOS and looking at galaxy clusters. And here on the right, I show our current bound, the dark blue, in comparison with the old bound using Leo T only. So we have a worsening of the bound, and this is mainly due to the fact that the profile for Leo T, the dark matter density for Leo T was overestimated in the previous analysis because of this, because from the data that was available at the time. Okay, so this brings me to my conclusion. So we have the strongest bounds in this mass range. We have improved on the robustness of previous bounds, and we also found no evidence for ALP dark matter. One may ask, how do you continue along these lines, where you can go try and do a similar analysis in the near infrared? You cannot go too much down in axion mass because the decay rate scales like mass to the third. But there have been already some forecasts from these two papers here, which forecast a sensitivity about about 10 to the 11th inverse GeV for masses in the near infrared. And thank you.
Thanks. Okay, questions? You can use the reaction button. Otherwise,
So Elisa, what is the resolution of the MUSE-Faint?
The energy resolution.
You said it can resolve the axion line. So what is the resolution?
It cannot.
It cannot.
No. It's comparable, but it doesn't quite resolve it. So, sorry, where is here? So the resolution in wavelength is here about 10 to the 3. I found that astronomers use resolution in the proper sense, like high resolution means a high number, not a small number, like you said, what we usually say. So high resolution and to the third.
I see.
Yeah.
Okay, so it's similar to the line.
Yeah, it's a bit larger because the velocity dispersion in the dwarfs is smaller than in the Milky Way.
It's colder. Okay.
Yeah.
Okay, thanks.
I'm curious about the targets that you used. Like, why did you choose those targets? Do you plan to have more?
Okay, so So the thing is that actually MUSE has other programs beyond this MUSE-Faint survey, which I don't know if they measure dwarf galaxies with these other programs, probably not. So this is a program target on ultra-faint dwarf galaxies. So they gave us sculpture, okay, and then they gave us ultra-faint dwarfs. They gave us more than what we included in the analysis. Actually, we have the data for more galaxies, but for those, we weren't able to find any information of the dark matter profile. So we couldn't use them. So for now, unless they decide to make new observations for now, I guess that's it. Or if somebody comes up with information for dark matter profile of these very faint other galaxies that they gave us, yeah.
Is there an assessment of the gas that's present? Like, is there such as you would overestimate the dark matter and make the result less robust? Sorry, more robust than what it actually is?
I think there should not be gas around in these dwarf galaxies. They should be quite empty. I don't know, maybe if there's a localized actually gas cloud that doesn't follow the profile of the dark matter, galaxy dark matter, probably it's not going to be a good fit. So I would say it's not going to make us overestimate the emission from dark matter, but yeah, that's what I can say right now. Yeah.
It would not degrade the bound by much.
Yeah, because if it's localized, it's not a good fit, I think.